All right, so now we're going to look at what's called the product rule and the quotient rule, continuing with our discussion of exponents, but we're still not including any variables. So it says, what happens when we multiply two powers that have the same base, okay? There's something very special that happens when we're multiplying when we have the exact same base. For instance, these two guys here, they're both powers. 3 raised to the second exponent, or 3 squared, and then we have 3 raised to the fourth power, but they have the same base of 3. Now, if we break that apart in terms of what they mean, the first one is saying 3 times 3, and the second one is saying 3 times 3 times 3 times 3, or 4 of those factors of 3 being multiplied, okay? But when we look at this all together, again, what we're multiplying here are these two guys together. So altogether, how many 3's are being multiplied here? Well, 6 of them, right? We're essentially multiplying 6 3's. So since we're multiplying 6 3's, what we're really multiplying is 6 factors of 3. Well, that's our very definition of what we talked about with our powers, is that the base would be 3 and our exponent would be 6 because that's how many factors of the 3's we're multiplying, okay? So we could simplify that to say that it's 3 to the 6th power, okay? Well, let's try that again with this guy and see if a pattern emerges. These both have a base of 7. So the first guy is really saying we have 7 times 7 times 7 times 7 times 7. And we're going to multiply that to what the second guy is saying, which is 7 times 7 times 7. Well, altogether, how many of these 7's are we really multiplying? Well, 1, 2, 3, 4, 5, 6, 7, 8 of these guys, right? So what we're really multiplying here in terms of the number of factors is 8 of these 7's. Well, again, that's the definition of what we talked about with our powers here, is that the base would be 7, and then I have 8 of those 7's being multiplied, okay? So that would be our exponent. So let's look at this and see if we have a pattern here. Notice the first guy, when we're looking at this guy, 2 plus 4 equals 6. And in the second guy, 5 plus 3 equals 8. So all that really happened here is that we added the exponents, and that was the end result that we had when we simplified, okay? That's called the product rule, which says I can add the exponents when we multiply with the same base, okay? So I can add the exponents together when we multiply with the same base, and that's going to be our solution, okay? So let's look at these guys here. So what this is really saying over here, if we have the same base of 4, is that I can add the 2 and the 4 together to get 4 to the 6th power. Now, that might be the answer that we're looking for, or if they want you to evaluate it, we could just break it apart as 4 times 4 times 4 times 4 times 4 times 4, okay? You can multiply that all together, or if you just wanted to in your calculator, take 4 to the 6th power, and we get 4,096, okay? Let's try this one. Now, notice, this does not have an exponent, okay? The first base here does not appear to have an exponent, okay? Well, anytime we don't have an exponent there, we treat it like it's 1, because really, if we look at what we talked about earlier in the last video, 3 to the first power is 3, right? So these two are equivalent to each other. So we can treat this like we have an exponent of 1. So if that's the case, when I have the same base here and I add these exponents, I'm going to get 3 to the 4th power, okay? So again, in our calculators, taking 3 to the 4th power, 3 times 3 times 3 times 3, we get 81, okay? Then we also have examples that might include more than more than just 2 bases here, okay, or more than 2 powers here, or one that involves a negative exponent, okay? So it's still the same rule here. We have the same base, so if we added those together, what's a negative 4 plus 3? Well, negative 1, right? So this would be 2 to the negative 1st power. Now, if you look at the instructions, they say we want to only have positive exponents. So this falls into what we did yesterday, okay? So now that we have a negative exponent, what we're going to do is the same idea. Treat this like it's over 1, flip it, 1 on top, 2 on bottom, raised to the first power. Raised to the first power. Now, that technically has a positive exponent, but we really don't need to write the 1. We could simplify it and say 2 to the first power is just 2, okay? Then over here, the rule still applies even when we have 3 of these powers being multiplied. all of these are the same base, so I can add all of these exponents together. So 3 plus 2 is 5, and 5 plus 2 is 7. So we keep our base, and we'd have 4 to the 7th power. So we're multiplying 7 of these 4s, or in your calculator, okay, we'd have 4 raised to the 7th power, which is 16,384. Okay? That's the product rule. Let's now look at the quotient rule and see if we can develop what's happening there. Okay? So what they start off with in this example is, again, the same base, but now we have division. Okay? Well, let's just write out what we have in terms of its factored form for both the numerator and denominator. So the numerator would be 3 times 3 times 3 times 3 times 3, 5 of those 3's. And we're dividing that by 3 times 3 times 3, correct? Well, that makes it really nice to simplify here, okay? In terms of division, we know that if I have 3 on top and 3 on bottom, 3 goes into 3 one time. Essentially what we're doing here is these guys would cancel each other out. Multiplication by 3 and division by 3 are opposites, okay? So they cancel out so that we'd be left with one on top and 1 on the bottom, but we don't really need to write 1 because 1 times anything is just whatever we're multiplying it by, right? So again, I also have another 3 and a 3 I can cancel out, another 3 and a 3 I can cancel out, and what we're left with is just 3 times 3 on the top, okay, in the numerator. So what we're left with is 3 times 3, and so we have 2 factors after, excuse me, after reducing here. Well, we know what 3 times 3 is. That's 3 squared, 2 factors of 3, right? So that would be my simplified expression. Let's try this guy. So we have 7 to the 4th power, so 7 times 7 times 7 times 7 over 7 to the 8th power, 7 times 7 times 7 times 7 times 7 times 7 times 7. Okay, so we have 8 of those 7s. Well, the same idea of reducing here is still going to apply. I can cross out these 7s, these 7s, these 7s, and these 7s. And what I'm left with, essentially, again, remember, when they cross out, essentially what's happening is we have 1 on top, 1 on bottom. So what we'd really have is 1 times 1 times 1 times 1, so we'd get 1 on the numerator, okay? And then 1 times anything down here isn't going to matter. We essentially end up with our 4 7s here, 7 times 7 times 7 times 7, okay? So that's what we end up with here after reducing, okay? So we have 4 of those factors after reducing. They just happen to be in the denominator, okay? Well, we can rewrite the denominator in terms of a power. The top will remain the same, but the bottom would be 7 to the 4th power because there's 4 of those 7s being multiplied. So that would be its simplified expression, okay? Well, notice there's a certain pattern that occurred here. 5 minus 3 is 2. And 4 minus 8 is a negative 4, okay? Well, let's go back here for a second. If I rewrote this so that the 7 was on top, remember, this is equivalent to 7 to the negative 4th power, right? Because I could flip it, and then it would be, if I flipped this guy over here, it would go to the bottom, and the exponent would become positive, right? So 4 minus 8 is a negative 4. So another way to say that, this is 7 to the negative 4th power, or if we wrote it as a positive exponent, this guy here. Okay, so the rule of this is when we're dividing, the rule here is we're going to subtract the exponents when we have the same base. So it'd be a to the m minus m. Okay, so we're going to subtract when we have the same base. So let's try this guy. We have the same base here in division, so we'd have 4 minus this 2 over here. Okay, so we're going to subtract those two guys. Keeping the base, 4 minus 2 is 2, so we end up with 2 squared. Okay, of course we could simplify that. That's 2 times 2, which is 4. Okay, let's try this guy. We have 3 as our base. We're going to keep that guy. And if it helps, you can actually write the subtraction on top. We could say it's 2 minus a negative 4, okay, because that's what we're doing is we're subtracting that negative. Don't lose that. But what happens when we subtract a negative? It becomes positive, right? So we get 3 to the 6th power. Okay, so it doesn't matter that we have a negative on bottom. You can still end up with a positive. So we get 3 to the 6th power, and to save us some time, if you want to, in your calculator, raise that to the 6th power, and we get 729. Okay, let's try a couple more. So again, we're going to keep our base here, and we'd have a negative 1 minus 3. Okay, well, what's a negative 1 minus 3? Negative 4. So we have 3 to the negative 4th power. But if we want to write that so that it doesn't have a negative exponent, what should we do? Well, again, treat it like it's over 1, flip it, and we have 1 over 3 to the 4th power. Okay, now maybe that's all they want you to do, or maybe they want you to simplify it further and say what 3 to the 4th power is. We could raise that on our calculator and we'd get 81. Okay, one last example here. Again, we have 2, a negative 1 minus 2. Okay, negative 1 minus 2 is negative 3. So if we want to write this with a positive exponent, what do? Put it over 1, flip it, and we have 1 over 2 to the 3rd power, 2 cubed. Okay, then of course in our calculators, we can take 2 times 2 times 2, and we get 1 over 8. Okay.